Alright, we're going to start delving into some pretty deep stuff here when we talk about quantum theory. So quantum theory, it relies heavily on equations. So a lot of the stuff that we're going to talk about were discoveries that were basically just made with a math equation. So scientists would look at math equations, they would calculate them out, they would do a graph or something, then they would realize, well, reality doesn't really match this equation, though, or what it should do. And so then they would rearrange their equation, they would try something else, and do it until they got it to match. And from that, believe it or not, from those equations, we've derived a lot of what we know about the atom today and its structure. So Max Planck in 1900 hypothesized that energy radiated from a heated object, such as a stove element or a light bulb filament, is emitted in discrete units, so unseen units or unseen quantities. And he called those quantities quanta. And so it comes from the root word quantity. So on the macro world, so the larger world, the way we would visualize this, or kind of the counterpart to this, would be a pot of water. If you put a pot of water on a stove and you heat it up and put a thermometer in it, you're going to see that temperature just kind of gradually climb up. Okay, so it'd be a steady increase in temperature. And so they assumed the same thing would happen at the electromagnetic world. So with those light waves that we talked about, the same thing should occur. Think of a light bulb. When you turn on a light bulb, okay, and it glows yellow, it gives off heat. You can kind of feel it by your hand giving off that heat, so it's radiating energy off of that light bulb. So they assume then if you were to change that frequency of the light, so remember yellow light is one frequency, if you were to change that frequency, increase it, well, the energy being radiated off should also increase proportionally, and it should make a steady increase up. But it didn't. Instead, it would increase by quantities, by quanta. So here's what that would look like. As we increase the intensity of the light, so as we turn up the energy of it, we would think that it would just go straight up like this. This is like the stove, okay? If you turn on your stove, as you increase the intensity, the temperature of the water is going to gradually increase. And you can watch that temperature on your thermometer just go up one step at a time. However, in all actuality, with the quantum level, with the smaller levels, with atoms and light waves and stuff, intensity, as you increase it, it only jumps up in certain quantities or quanta. And this was troubling to scientists. They did not expect to see something like this. That would be like putting a pot of water on your stove, turning it on high, and then watching the thermometer go from 0 degrees up to 5 degrees. No 1, 2, 3, or 4, just right from 0 to 5. And then it jumped up to 10. No 6 through 9, it just went from 5 to 10. And so instead of gradually increasing, they would jump up by certain quantities every time. This led them to believe that energy came out in discrete units, so small amounts, and it had to be somewhere within those small amounts. They called this then the quantum theory. So it's a lot like your stair steps. If you walk up steps, you can't step somewhere in between. So it's not like you can stop and stand right here. You either have to be here, 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 or here. Okay? So the amount of energy you have to expel is always the energy to go from one step to the other. If you don't expel enough energy, if you only expel enough energy to go to like right there, you're not going to get up to the next step. You're just going to stay down here. So then one quantum would be the amount of energy, or each step, that you would be required to go up one. So you can't increase the energy of light by a fraction. It has to go up by one quantum or not at all. You can't do like half a quantum or 0.25 or even 0.99 quantums. It's got to be all or none. So if you take something like, let's say, yellow light waves, and you increase the intensity of those yellow light waves, and you measure the energy output, it will not gradually increase. Instead, you're going to see jumps. So at first, it's going to have this amount of energy. Then it's going to jump up and have that amount. Then that amount, that. So it'll go up steps like that instead of a gradual increase. This is very, very much different than what we see in the large world. So as a result, we can't measure energy the same way we measure frequency or wavelength. Since frequency and wavelength, they gradually increase from one to the other. We can use that other equation. But energy increases based upon quantums. And so Planck came up with what's called Planck's Constant. And so energy is not directly related or directly proportional to frequency. If frequency goes up one step, energy doesn't go up one step. It has to increase by those discrete units. And so Planck came up with this number right here, 6.63 times 10 to the negative 34th joule seconds. He found that he could use that then to calculate the energy for a particular frequency. And so look at the units on this, and we want to make sure that those all match. So energy has to be in joules, okay, because Planck's constant is in joule seconds, and frequency is in seconds inverse or hertz. And that way joules can cancel out joules, and seconds can cancel out seconds. All right, so make sure you always put your units on everything. And also what we can see here is that each quanta in a high-frequency light, like violet light, contains more energy than quanta in a low-frequency or red light. So that means that if you have a higher frequency, so if your V is higher, that means you're going to multiply this number by a higher number, and so you're going to get a larger jump in energy. So the steps then aren't even like we saw in that last picture. So if we have a higher frequency wave, that means its step up is going to be higher, whereas a lower frequency wave, like a red one, is going to be a smaller step. So those discrete units aren't the same unit for each individual step. It depends on the frequency of the light. But the amount of energy change between red and yellow isn't going to be the same as yellow and purple. And that's because of that Planck's constant. So science is really just nerds playing with toys, and when they play with those toys, they make new discoveries as a result, and they publish them in papers, and we all get a little bit smarter. So one of those nerd toys was the photoelectric effect, which what you would do is you would take a metal plate, okay, so this is just like a sheet of metal, and then you would have another sheet of metal over on the other side called a collector plate. And if you shine light on a metal plate of a certain intensity, electrons will fly off of it, and so it would cause them to fly off and hit a collector plate. So instead of just scattering around, you would get these, that would be a fairly close distance right there. So those electrons could jump over there, and then we'd use a battery to kind of pull them through. And so as a result, you would wind up with a flow of electrons through this circuit, which could light up a lamp, and then we could also measure the voltage on there. So you shine lights on a metal plate, forcing electrons to jump over into this collector plate, and then that flow of electrons is what we call electricity, so you get light bulbs and stuff. So this was something that science knew about, and so scientists would literally sit in their labs, play with this thing. They would do weird things to it to try and make it behave strangely. That way they could figure out, well, why is it behaving strangely? And then they can make new discoveries based on that. And what scientists thought caused this was you put energy on there, the energy kind of builds up with those electrons, and they fly over there. And so if you shine light on it, you're going to give those electrons energy, and eventually they're going to jump up. So playing with their toys, they decided, well, let's shine just certain frequencies of light, so certain colors of light on that metal plate, and see what happens. What they found was when they took a low-frequency light, like a red-colored light, okay, that has a low frequency, it did not eject any electrons, even if you shine it on there for several days, and even if you used a highly intense one. So that means not just taking a red light, but taking a really bright red light with tons of intensity flowing off of it and hitting it on that metal plate. It still would not eject any electrons. This would be like taking a pot of water and putting it on the stove and setting it to medium. It'll eventually boil. Okay, it just takes longer than if you were to set it on high, but at some point it will boil because you're giving it energy. And so you would think that if you set this high-intensity light on there, even though it was low frequency, eventually you would give those electrons enough energy to where they could fly over. But that was not the case. So this is what scientists try to go for. They try and find discrepant events so that they can explain why it's happening. So what they did next is they slowly changed the frequency of the light. And there would be a point that it would hit, and suddenly those electrons would start coming off. So once it hit a threshold frequency, okay, at a certain point, and it's not like they would gradually increase and slowly start spitting off a few electrons and the number of electrons would increase. No, it was like on-off. They would hit a frequency, and bam, those electrons start flowing, the lamp would turn on. Let's say the threshold frequency was something like 5.5 times 10 to the 14th hertz. Okay, and let's say you were shining a light on there that was 5.499999 times 10 to the 14th hertz. You could shine it on there for days, and it would never fling a single electron. But the second you turn it up to 5.5 and hit its threshold, it will instantly start throwing those electrons over there. Lamp comes on. This would be like taking that pot of water that's on your stove, turning it to medium. It never boils for days. You turn it one click up and suddenly, bam, the entire pot is boiling. It doesn't happen like that on our scale. But here at the electron scale, something is different, and it's those quantums that exist. You hit that particular quantum, and suddenly you are able to go to the next step. Fact, increasing the intensity of the light will not change the velocity of the electrons. So one would think if you turned up kind of the power of that light, that threshold light, that the electrons would start flowing off faster. So you're giving it more intensity, so the electrons are going to fly off harder, and they're going to hit that collection plate with more force. They don't. You get more electrons to come off, but every single one of those electrons will share the exact same velocity. So they fly off with the same force. What that tells us then is that intensity is not equal to energy. Energy is a quantity that does not fluctuate until you hit another point, until you hit another quantum. So increasing the intensity of this light only ejects more electrons, so you're able to hit more electrons, but it does not increase the energy. And here's the last fact. If you increase the frequency of the light, so not the intensity, this time we're increasing the frequency, and remember frequency changes the color of the light, eventually you will hit a point where you hop up another quantum, and now the electrons will come off with a different speed. And so you can change the speed of the electrons by changing the frequency, but they don't gradually increase their frequency, instead, or don't gradually increase their energy. Instead, you eventually hit another point where new energy coming off, but they all come off at the same velocity at that point too. So what that told them then is that frequency is related to energy, not the intensity. So what we kind of visualize when we see a brighter light, we might think that's more energy, but it's not. And what this did then is it helped us kind of verify what Planck said. So Einstein then took all of this information, all of this evidence that we've seen, and threw it together in what's called the light theory. One of the biggest revelations from the light theory was the term photons. So photons, he said, was a beam of light is a stream of particles then. So instead of light being like a solid beam, so when we think of light, we may think this solid wave of red or whatever color coming towards our eyes, but it's not. In order for all this evidence to match up, in order for us to have quantums and this photoelectric effect, light actually needs to be in small, discrete particles. So when we see light, we actually see these tiny little waves coming towards us. And, there's tons of them. So when you flip on a light, it's not like beam, boom, 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 single particles of light coming towards us. There's thousands upon millions upon trillions of these all coming at once. And so we see it as a solid beam coming towards our eyes. So when we think of as a quantum, is actually just a particle, a photon. So then a quantum of different energy states would just be particles with different amounts of energy. So you might have a quantum with that much energy or with that much energy. But in order to keep with the quantum theory that it kind of goes up in the stair steps, you wouldn't have a photon in between those two energy states. Okay, so it's either one or the other, and it has to reach a certain threshold in order for it to go from this energy to this energy. And so then what they were observing in the photoelectric effect was in order for the electrons to be ejected, you had to hit a certain energy of light or a certain frequency of light. So if you were giving off this much energy, maybe nothing would be ejected, but then once you hit this one right here, that would be the threshold, and then the electrons would start being ejected. And this makes sense, because if energy were just a constant beam, and you were to hit electrons with it, it would eventually absorb enough energy to where that electron could be ejected, but they're not. Remember, when they were hit with the energy, even if you left that light on there all day long, it would not eject electrons until it hit a certain threshold. So that means you give it energy. So if you're giving it this guy, this guy, this guy, this guy, this guy, it's never enough to send it up. This is like trying to kind of push a baseball up a stair. If you just lightly pat it over and over and over again, it's never going to go up those stairs no matter how many times you pat it. You have to hit a certain threshold where you give it enough energy where then it can bounce up all the way. So from this, we now recognize that light is not a continuous stream. Instead, it's these photons, these quantums of energy. So looking at this equation again, we can use it to find the energy of a single photon as well. So this is not the energy necessary to the entire wave, just one of those little particles that's coming off, one of those little light waves. Okay, I'm sure this is a lot to take in. This is very deep stuff. We're looking at things that we don't normally talk about and things that we can't really see with our eyes. In fact, this is delving into a lot of physics-based research. What I recommend doing, make sure you read this stuff in your book, read it in your PRG, even type this into YouTube and you'll see all kinds of great animations and videos that'll do a better job of explaining it than what I can do with a PowerPoint in a couple minutes.